1980 Problem M3. Now, this problem revolves around a billiard ball and its motion directly after it's been struck by a cue. The first step requires us to find the translational velocity. Okay, so our general form for the equation is v final equals v initial plus at. In this problem, the acceleration is provided by the force of friction. Using Newton's second law, we have acceleration equals force of friction over the mass. Now, our force is going to be equal to mu mg, so that's mu times the normal force. However, it's important to note that since friction is slowing the ball down, in our system, we should label it negative. So the force is actually negative mu mg. Divided by the mass, we get an acceleration of negative mu g. When we plug that back into our expression, we get v final equals v initial minus mu gt. Now, the second part of this problem requires us to find the angular velocity. Now, angular velocity can be found by finding the angular acceleration. That's given to us by the torque. Now, torque is either the cross product of radius and force, or it's the product of the moment of inertia times the angular acceleration. Using these two representations, we can solve for the angular acceleration. Now our mu mgr divided by our moment of inertia gives us an acceleration in the angular direction of 5 mu g over 2r. When we plug that into our general form, we get omega final equals 5 mu gt over 2r. Now the third step of this problem requires us to find the point at which the ball begins to roll without slipping. Now this will occur at the moment in time when the velocity in the translational motion times the radius equals the angular velocity. Now, using the expressions that we came up with in part A and in part B, we get r times v initial minus mu gt equals 5 mu gt over 2r. The r's cancel, and you can solve for t. Now, it's important to notice that mu gt and mu gt become two constant values, or rather same values, so you can combine them into 7/2 mu gt, making it much easier to solve. Now, the final part of this problem is to understand why the angular momentum about the point P, which is where the ball makes contact with the billiards table, doesn't change after it's been struck by the cue or as time progresses. Now, let's think about it this way. Since the force of friction goes through point P, which is again the point where the ball makes contact with the table, there can't be any torque because a force through the center equals zero torque. Since we have zero torque, the change in angular momentum over the change in time must equal zero. By basic principles of math, we know that now the angular momentum cannot change, or rather the change in angular momentum must be zero. Therefore, the fact that the friction passes through point P makes the angular momentum through point P remain constant. That's all for this problem. Catch me in the next one. See you guys.